Okay, welcome everyone to my talk about Goodbye Electron, Hello Tauri plus Rust. A little bit about myself. I'm a software developer since 2009. I've been working mostly in the C++ audio processing real-time world. So I'm not really into this web framework necessarily directly, but I have been making a lot of user interfaces, and most user interfaces that we make in our company needs to have some form of interoperability with the customer, and it usually is based on web, at least from our side. So in our work, we kind of touch upon that all the time. Today I'm working in a company called Squarehead Technology, and we are making a product that is a microphone array. Basically, you have the hexagon-shaped array here. It consists of several hundred microphones, and with that technology, we can pinpoint where sound is coming from. And that way we can kind of make an image of sound, and we can do tracking in the sound based on frequencies, and we can start finding audio objects. So this is a completely embedded product that we make in our house. With this, we combine this with machine learning technology, and then we can try to figure out what kind of events or classes these audio events are. So we have this drone detection product, and we also have artillery detection products that we make with the same technology. And we also make products within other kind of industries. We do it for industrial purpose to find anomaly in high decibel level environments, basically, where microphone arrays have a thing. So back to my talk. Basically, every product that you make, if you're making an embedded product or you're making something that is really smart, you need some form of way to present that to the user. And since we are making these embedded things, we do always have to wrap these things around something that can make this interactability with the user. And I've been doing this for many years, so we've done this all through kind of, you can do native development, where you do a native C++ engine, for instance. I've been making Linux GTK applications and Mac OS applications and all these things. And every time we do this, it always comes with a cost that, okay, we only target one platform and not the other platforms. And if we want to move the same functionality to different users, you have to do it again, at least. And I hope to give you some examples here with some cross-platform frameworks that you can use for that purpose, where you only have to write once to reach all your users. So I will go through kind of the state of what are in this world of cross-platform desktop development. I'm going to talk specifically about Electron, because that has kind of became the standard for that purpose. I'm going to go through how Tauri can be a better solution. At least it addresses some of the issues that we have seen with Electron. And I'm going to use Squarehead's kind of adoption to Tauri as some examples, because we have already started using Tauri for these kind of applications so that we can move faster in the development process. So it's 2025. Why do we want native desktop development anymore? Aren't everyone just using web now? So you have the cloud, you can make a software as a service kind of solution, or you can just embed a Webview on your embedded product yourself. So is there any need for this? So I'm wondering, how many of you are actually writing native desktop applications? We have some. And what frameworks are people using? Who is using Qt, for instance? Qt, yeah. Who are using Electron? No one. It's more like in the web. Oh, yeah, we have one. And are anyone using Tauri already? No. So Qt is kind of one way of doing that, and it has been around for very many years. And it's a very good framework for that. But you do need C++ developers to write that. And often I find it easier to find web developers to hire for that purpose. And I think it also moves a bit faster with the web development. And that's why there has kind of been a major shift in the past few years where web developers tend to want to reach beyond just the browser. They already have this cross-platform dependency, and they don't really see why they can't do that with a desktop at least. So they increasingly want this desktop reach. They want to build with the same technology that they can use for all the browsers in the world. They want to just, okay, if we do need a native desktop application, why don't we use the web framework for that? And we do want a native app because in many ways you do need some native functionality. And very often you want to interact with the user in the most natural way, and they're used to kind of using the window technology, the menus, and everything that they are already familiar with. And you also sometimes need to interact a lot with files on the system. You want to maybe access some USB devices, and you want to touch upon things that aren't that easily done through the web only. In addition, when you do write the software as a service kind of thing, you're kind of online. And in many cases, that is not always possible. You might want to have something that works in an offline state as well. And as you see, we come from the defense industry, and giving them something that relies on internet is not an option. And that is in many other applications as well. And I think also that if you do rely on performance, you still might want to have a native application for that as well, where you can utilize more native code and closer to the hardware. In many years, Electron became the default and kind of solved this cross-platform development and kind of stepped in. I think it kind of came in at the right time, and it kind of became the standard just because it provided the solution. And I think that's kind of why it has kind of gone into this default mode where, oh yeah, you need cross-platform development. Okay, go for Electron kind of state. So isn't the solution then to use Electron? I would say yes, in many purposes you can do that, and I think it's a very good tool for that. And I will go through a bit about Electron before I touch upon maybe some of the issues with Electron. So what is Electron? So Electron is kind of very easy to start tech stack with the Chromium engine that you build into your application, and you use the Node.js as the framework for the backend, basically. It's very similar to a server architecture where you have a server hosting a frontend, basically, and you can write the server backend in the Node.js language, and then you write the frontend in whatever you choose of the front-end language, React, Svelte, Vue, whatever. And it's very familiar from this front-end perspective, so it's a lot of web developers will recognize this pattern immediately and kind of, oh, this is great, we can do this. And we can make an app very easily just by using the tools you're already familiar with. So you write the same language in the backend as well as in the front-end. Basically, it's based on JavaScript or TypeScript type of language. So you don't really need to learn two languages to write both the backend and the front-end. So it's convenient. It was released in 2013, and it was originally called Atom Shell. Was kind of the before it kind of migrated into this Electron name a few years later. So And to be honest, Electron has a huge adoption. So almost every app I use and I find is used out there is using Electron. So here you have some example in Discord, Microsoft Teams, Figma, Tidal, Splice, Slack. All of these are using Electron today. So it's essential to know that Electron is a very good tool for actually making these. And there are lots of great apps out there using Electron and working great with Electron. So I say goodbye to Electron, so there must be some pain points to the Electron. And yes, there are some things with Electron that people tend to not like. So I'm going to go through a few of them. So you have, this is just for, this is kind of a benchmark, but it's not really a benchmark. It's just my way of kind of seeing this issue. So this is running on my Mac. It's the Hello World example from both Tauri and from Electron, running with activity monitors. It's not very scientific at all, but this shows just the default memory usage of a standard app, basically. So you have the Tauri app on the left side, you have the Electron on the right side, and immediately you see that this starts off with using a lot more memory than the Tauri side. So this is one of the critics of the Electron, that it's using a lot of memory and tends to seem a little bit heavy, kind of when you run it. So this is one of the pain points. So the other side is kind of the bundle size of Electron. So if you compare Tauri with Electron, you see it's a huge difference, basically. And this is due to that when you build Electron, you have to build in the whole Chromium engine, browser engine, within your application. So kind of you pack the whole Chromium and you ship that to your customers. While Tauri does it in a different way. I will come back to that. So that means even if you make the tiniest little app that you just want to do one simple thing, so you still have to ship 263 megabytes of application to your customer. It's not necessarily that bad because everyone can download pretty large sizes today. The next issue is kind of the one that made us not choose Electron, and that's more the security concerns of Electron. So every time you make this backend, frontend, in communication between the backend and the frontend in the Electron app, you have to kind of set up a system that where you can communicate between the processes. So it's called inter-process communication, IPC, short for that. And that Node.js bridge that you send back and forth data introduces a vulnerability vector. It's not impossible to make it safe. So you can make it safe. But I think the code and the framework makes it too easy to make something that isn't secure. So I will give you some examples of what I mean by this. So this is just a very simple example. This is the front end on the Electron app using TypeScript. So this is kind of one way of sending data. So you can call the require Electron and you get the IPC renderer. This is the front end part of it where you can send data back to the back end of the application. And you call send with a command and some parameters, basically. On the back end, you can do the same. You can listen on this event, and you can do something with it, and then you can send it back, basically. And then the front end can listen for that response, basically. And it seems pretty straightforward, yes. Works pretty nice. But the problem is that if I can write something that says require Electron, why can't I just embed a third-party library where I use the require Electron and I start listening on your app? Because you use my third party and then I can suddenly interrupt the communication. So that's kind of the thing. And this is legal to write in Electron. It's not recommended, but it's legal. So you can do this. And this is the other way around, so you can also just have the backend send messages to the front end where you send status updates. So this is just when you loaded the web window, you send, okay, we're connected, the backend is ready, and you can on the front end listen for that message. So both of these kind of are unsafe ways of doing it, but completely legal. And it's due to that there are some parameters that when you build the application, you have to kind of set them correctly to make all the security parameters right. So when you have the node integration to true, you enable the require in the renderer, and that makes every front-end script possible to call the require. And also you have this context isolation, which kind of is what you need to set to protect the front end to actually expose these APIs that you can use to call back and forth. So to fix this, you have to kind of do you have to put a preload JS and basically create your own API, and you have to flip the switches of the booleans so that they're true, and okay, now we're good, because now we made this thing. Okay, I'll write my preload JS API, and that works, basically, if you do it exactly like that. Because then you can have, on the front end, you can get this Electron API where you can start calling things. And this is the safe way of doing this, because the preload is only injected into your code, basically, and not other code. But still, in this way of doing it, you can do this, which is you just expose the IPC renderer directly. So it's still possible to just do the wrong thing. Even though I made this secure thing, I can just, okay, I just make the API a bit simple, so that it's more flexible on the front-end side, you can say like this. And this also exposes a security risk, because you've exposed the IPC render on, and then you can start using that one as an attack vector into the application. And also, if you even try to do it right, but you expose the event from the callback, the event's parent actually owns the IPC renderer, so even that is unsafe. So it's not that it's, so the point is that it's completely fine to do this safe, but the library isn't really helping you to make it safe. You have to kind of know about these things, you have to read the documentation, do the right thing, and then you're safe. So that's kind of the Node.js bridge vulnerability in the Electron framework. The other vulnerability that I will bring up is the Chromium security concerns. Because when you make an application in Electron, you have said, okay, we take the whole Chromium framework and we ship that to the customer. And basically, that means you're the browser vendor now. So if Chromium engine has a 0-day bug in its code, it's your responsibility to fix it, because you've shipped version XYZ of that library, and if that contains a vulnerability, you have to fix it. So the shipped Chromium is basically your responsibility now, and that means that you have to patch it and make sure you're up to date with that one. And you need to make app updates with all the security updates coming from the Chromium yourself. You don't get any help from the operating system with this. It's your job to do that. And that means you have lots of continuous updates that you need to be aware of. You need to follow these things. And it leads very often to a developer fatigue, where you need to kind of maintain this all the time. And I also believe you get a user fatigue, because you have to ship updates of your applications all the time. So every time you launch the app, there's a new update. Okay, I need to update. And then people start skipping the updates, basically, because they're too tired of that. And just to indicate a little bit, so here's a very list of the latest patches on Chromium for the last month and a half or something. So there's a lot of things going into this. And the major app vendor that has used Electron has solved this issue by just releasing at dates, basically. They have, okay, every month we release an update because we just have to continuously deliver new updates, and you just do it on date. But and that's the big companies, basically Slack and such, they can do that. But if you make an app of that, you have to do the same thing, and maybe that's not something that suits the development process in your company. All right, so that's Electron. So what is Tauri then? Is that just another framework coming with its own flaws, or does this solve kind of these issues that we have with Electron? So a little bit about Tauri. So Tauri is kind of a framework for creating cross-platform applications. It's pretty similar to Electron, but does it in a somewhat different way, basically. So you can access all the information on that website, tauri.app. It's in version 2.25 now, and it's been around since 2020. So it's a bit newer and hasn't been around that long. So the adoption for Tauri hasn't come that much yet. But I do believe the Arc browser, for instance, is built on Tauri. I do believe that's, and there's coming up more applications that kind of built on this framework. So how does Tauri work under the hood? So it wraps two Rust libraries, basically. So it wraps the Tau library, which is a library that is written in Rust to handle window management in an operating system. And this is a cross-platform library, so it operates on all major platforms. It also has a VRI, which is the wrapper around the system Webview, basically. So that's why it's called Tauri, because they say Tauri. Yeah. So that's kind of where the name comes from. There's definitely more Rust code underneath, and the Tauri includes a lot of Rust code in itself as well. But these are kind of the frameworks that it kind of based on. And it has support for Windows, Mac OS, and Linux. Very similar to Electron, so you can build the application once and ship them to all of those. It does also have additional support for iOS and Android. I have not tested that one, and we have not kind of gone that way in our company yet, but it is a thing that we're looking for possible use of in the future, because if we can build everything once and we can ship on all devices, that will be amazing. But I don't believe it until it actually works, but because mobile tends to be quite different from desktop, and I don't always think that it makes sense to build something that targets all, but yeah, maybe in the future. So the web framework of Tauri is kind of, you have a lightweight native shell that is built on this Tau, and it launches a Webview within that window, basically. And it depends the system Webview instead of Chromium. And so the Chromium is not included. You use the OS own rendering engine. And every operating system has one web rendering system already built into the operating system. So for Windows, it uses the Webview 2 framework, for instance. For Mac OS, it uses the WK Webview framework, and on Linux it uses WebKit GTK, basically. So it uses whatever is on the platform, and I think that also says it uses whatever is optimized for that platform as well, because these frameworks are the OS, part of the operating system, so they are optimized for that platform. They're kind of secure fixed through the operating system, and that means kind of, I think that could be a better solution. There are some negativity to that as well, because when you do ship the Chromium in Electron, you kind of only need to test your web code towards the Chromium engine. While on this one, you actually have to test on this. And there might be some differences, and you might have some issues with this, but it's pretty similar to actually launching a website, because then you already have to test against multiple browsers, and this is similar to that kind of job, basically. And I think you always need to test your application on all the platforms that you want to deploy anyway. So Rust powers the backend. So basically all the backend of the application of the Tauri is in Rust. There's no choice there now. I know there's some talk about embedding some C++ there, but there's nothing that works yet. And basically you can choose whatever framework you want on the front-end side. React or Friends is what I'm saying. So React is the most common, I think, but there are multiple versions of web framework that you can use that powers the UI. And for me, that's one of the good things about this, because I do believe that the backend should be in a performant language, and I think Rust is very performant for this purpose. But I do believe also that the front end has an advantage that it comes from the web world, because I think the iteration of developing on the web platform is faster. And I think you can move faster, and then I also think you can use also different engineers for that as well. So you can have people excellent in web and user design can work on that part of it, and then you can have other people working on the performance thing. So I think you can say it's a very good mix of performance and flexibility in that combination, basically. So I talked a bit about the secure thing in Electron. So what has Tauri done to kind of prevent the same vulnerability? So Tauri has come with this as a target when they made this framework, basically. So one thing that you can kind of expose in more detail than what you could in Electron. In Electron, you could, for instance, say that, okay, I want file system access. But in Tauri, they have gone with the same kind of permission, but you can say also specify where in the file system you can do. So you can even aim your application. Okay, I want only for the configured directivity or something. You can specify exactly where you want this application to have access. So you have more fine-grained runtime permissions that you explicitly have to set. So you can design your application to not do stupid things. It has secure IPC via message passing. So basically, it does not use share memory. So it uses two processes and sends data back and forth between the backend and the front end. And both of these are written in Rust. And basically, that means that it's easier to kind of reject unauthorized or malformed messages in that process. And there's no shared memories. You can't actually exploit directly, at least, if you send something that is not the correct thing. It has an invoke key protection, and that means when you do build your web code with the Tauri framework, it injects an authorization key into your front end and the back end. So that means when that key is compiled in and you built your app, it's not exposed anywhere else. So if you do have some rogue scripts that suddenly come into your application somehow, they are not built with the same invoke key. So that means that it's blocked directly if you don't have the right access key to it. It just blocks iframes and other origin restrictions. There's no workaround. So you can't do that, basically. So that just minimizes the attack surface that you have in your application. It's built on Rust, so we all love Rust, so it's safer by design, I think, and at least if you compare it to the TypeScript Node.js framework there. And there is also ongoing security audits, so there are regular third-party audits on the releases of Tauri, so that they at least have a mechanism for addressing security concerns with each release. So a little bit details about this fine-grained runtime access. So this is kind of just an example of, you have a tauri.conf.json file that you need to specify what you want to give access to in your application. So in this example, you have, you say something about the FS file system. You say you can't reach all, you can read and write, and you can write it within this config scope. And you have to write it like this because it's cross-platform, so config means some different paths on the different operating system that Tauri has chosen that this is the, so on the Mac, for instance, you have user library, application support, and app name, and you have the different on the other. And you can also do this even more specified. You can kind of do the scope by setting just, okay, config with this directory or some other directory. And that means that you're allowed to access just that one, but you're kind of not allowed to reach any of the other file system locations on your system. So if you look at how the Tauri architecture is, so you have the user interface, the Webview, Rust core, and the OS. That's kind of the main parts of the Tauri framework. And the Webview and the Rust core has this message passing, so the IPC communication. And you do that via the invoke command from the Webview to the Rust core. And that means that you have invoke, and that command maps to a Rust command. And the other way around, you have a Rust can emit events, and the front end can set up a handler to kind of respond on that event. So that means you have the full circle of communication between the front end and the back end, which you do need to make an application. At least if you make an application that does something with the operating system, like reading a file, writing something, or running an algorithm in Rust for encryption, or something that Rust is suited for. So some code examples. So here you have the TypeScript side, where you can import this @Tauri apps API core, and you get the invoke from that one. This is what I'm talking about when I talked about the invoke key protection. If you try to do this and you don't have the invoke key, it will just fail with an exception. So you can't do that in any third-party library that you include or something from a different source than what you have already included in your application. So, but if you are in your application, you can use this invoke, and you can send greet, and I put my name in there, name Andreas, and you want to do something with that and listen for the message, and I've just done a console log here. So, on the REST side, you have to define your API, basically. And to define the API, there are some things you do need to make correct. So you have this hashtag Tauri command macro, which is what you kind of mark it as this is going to be exposed. And you write a function signature, like the one that you want to have. And you see that it says, okay, it takes a string, and it does something with that one and returns that with this format exclamation mark macro. And in addition, you have to kind of map this into the invoke handler as well. So you have to put it into the API when you build the application. So you put in the greet function that you mount into the invoke handler. So this is what you do to allow the greet command to be allowed to call from the front end, basically. When you do this, there's the strict type checking. So if you do greet with a capital G, for instance, you type something wrong, it will fail on the JavaScript file side. And it actually will give you a good error message, actually. Command greet not found. So it says something about that, okay, this is not working. And even if you call greet and you don't have the function signature right, where you miss the parameters, for instance, it will say invalid, unhandled promise rejection, invalid args name for command greet missing required key name. So it actually kind of gives you a sane error message, and this is kind of the malform message rejection that Tauri handles for you. So you have to be correct, basically. For the other way, this is how you do the listen. Same with the @Tauri apps API event. This is blocked if you don't have this invoke key. So you can't do this in code that is not your own. And you call the listen, and you can respond to an event there. And from the Tauri side, you do the same here. You call window emit, and then you can send the message back to the front end. You see that you call it on the window. So basically, if your app have multiple windows, you can choose which window you want to call back, basically, or send messages to. So that's kind of how it works. Okay, I'm going to talk a bit about how you build the Tauri application. So when you have kind of made your application and you've written your source code for both the Rust and the front end, the build process is that you compile the front end, React, or usually you compile it. You don't need to because it depends on what framework you're using. But I would recommend that you use TypeScript and compile it. And then you compile it to static files. So that's basically HTML, CSS, JavaScript, these compiled units that you use in a typical front end. And the Rust side, you compile that to a single library. So all the Rust code is compiled separately from that. And then what you do in the end is that you bundle these two together. And so they're not it's not like a library and then a lot of CSS, JavaScript files in your application. They're compiled into a binary. So everything is in that binary. So in the application, you have then a native executable, and the web resources, when you load the application, is already in memory. So when you load the application, you have loaded all the web resources that you need to present your view. And this is kind of essential for having an app that has native feel, because you need it to be fast and feel good. And when you have everything in memory, it's very fast to load all these resources. And that's why it feels a bit faster when you open that application. The view is there, basically. So to show you just this is how an application bundle on Mac OS looks like. You have the boilerplate with the plist and the icon that is required for a Mac app, but everything else is in one binary, basically, when you ship the application. So that means that you have when you build this, you have a native app ready for distribution. You have a self-contained single executable that contains everything you need for your application. It's smaller, it's faster, and it's fully offline capable. So nothing is kind of loaded. You don't have this Electron where you run your own little server within the application and just loads it from there. Everything is just in memory and fast. You do get cross-platform installers for Windows, Mac OS, Linux, like you should. So you build it to the .msi, the .dmg, or the .deb, which is what you need to give it to your users. And you can run it to the the signing for each platform that you need to securely distribute and update your application. So that means that you can build it directly and run it and provide it to your customers. There's another thing that we in Squared tend to use in the Tauri framework, and that is what we refer to as Sidecar in Tauri. So a Sidecar is basically another application that you want to run because you want it to also use something else that you have made. And this is essential for us in Squared because we have a lot of C++ code. And we have a lot of audio processing code that we already want to utilize. And basically, with this Sidecar process, we can combine the application, the Tauri application, with some other application that we already have to run certain things. And in Tauri, this is kind of built-in thing into the framework so that you can actually embed other applications in your application. So how you do that is that you can specify that you have some binaries that you want to include when you distribute the application. You just define it like that, and in the Tauri code you can choose whether you want to run those sidecar applications from either the REST side of the code or from the front-end side of the code. So you can choose what fits in your application. So some examples of how you can do that. So this is Tauri, this is the REST side running the sidecar. So you can spawn this sidecar and start. This is like a daemon. So you just launch a daemon next to your application that does some handling. For us, that will be, for instance, talking to the microphone array, getting all the microphone data to your application and process it to some form of audio that you want to present in your application, basically. If you see the same examples, this is more like a one-shot example. This is from the front-end side. If you just want to, okay, I have a CLI that I just want to trigger sometimes to do certain operations, for instance. You can do it like this. You can execute it and then get the standard out, standard error, whatever from that one. And you can also do the daemon spawning from the front end itself, so that you can start it from that side as well. But there are some caveats to this, because how about architecture and platform differences? Because if you have a cross-platform and you want to have a sidecar, isn't that conflicting in some way? Yeah, it is. So don't do this if you don't need to, because if you want to make the sidecar work on Mac OS, Linux, and Windows, you have to actually build an application for all those and pack the right version and maybe the right architecture as well. So I would not recommend to do this if you don't need it, but in some ways it might be necessary. Let's say you build an application that does image processing, for instance. Maybe you want to include ImageMagick, but you don't want the user to install ImageMagick, for instance. You can pack the ImageMagick CLI into your application and just use it within that application, for instance. So it opens some flexibility, but yeah, there are some things. And you should be aware that if you actually make this sidecar and you say you set up a socket API or web API or something that communicates to the front end, you have basically disregarded the REST security. So you should be aware of that and maybe not do that. Or maybe do it, but do it in a secure way at least. So to just summarize a bit about the differences between Tauri and REST. So the major issues that you can see is the bundle size is larger on Electron than on Tauri. You have the runtime Chrome plus Node.js, and you have the native Webview plus REST on the Tauri side. Memory usage tend to be higher on Electron and lower on the Tauri side. The security model, I will say loosely sandbox is what I will say. You can get it right, but it's not really always right. And you have the IPC bridge and REST safety, where there's no way of getting around that, basically. You have the NPM ecosystem on the Electron. On the Tauri side, you have REST crates and plugins where you can use the standard REST libraries like Svelte, Tokyo, and these things, and also some Tauri plugins that can help you do things. You have the sidecar support. You can obviously do that in Electron as well by packing it, but it's more built into the Tauri, and the language is front-end is JavaScript, TypeScript, and the backend is JavaScript, TypeScript, and REST on the Tauri side. So this is kind of the comparison chart of this. Okay, so why did Squared adopt Tauri? As I said, we make this product, which is a microphone array. And it consists of very many parts of the system. So we have hardware for sampling microphones. We have hardware for getting cameras working, GPS working, maybe some human-machine interface on it. But in principle, there's a CPU inside there that runs our code, basically. And that code is based on our tech stack, which is basically, we have a Yocto operating system. We have a C++ engine that does all the data handling and storage and processing. We build an API on top of that one. And what we have had until now is that each device has their own web interface, basically. That has kind of been our tech stack. And that's a very flexible tech stack, and it's a natural one, basically. So it works really fine when you want to access one of our microphone arrays. So this is just one of our user interfaces that looks at the fan in the ceiling, seeing sound, for instance. But the problem is, when you do have multiple arrays, okay, should I have one view from each? Doesn't really work. Or okay, I can access one of them, and they can send data from the others, for instance. So I can access it through this API bridge, and they can say where the other are. Okay, so it works kind of. We made some UIs like this where you can kind of combine data streams from multiple arrays, but still within one web browser. Okay, it works. But then suddenly we start accessing things on different networks, and they don't really know about each other. And then we start to see that there's an issue. Okay, we need to have one client on each of the connected arrays. We can't really combine it. There's an obvious solution. You can use the cloud, for instance, where you make the arrays connect to the cloud. That solves the issue. But I've told you already, we're in a defense industry, so we can't really use the cloud or internet for anything. So that's not really an option for our case. So that's mean we have to do some architectural change. And that's where we kind of saw, okay, let's move the web interface out of the embedded device. That can be an option, because then we can at least access the APIs from each of our sensors and create a unified user experience when you look at the whole system, because we're expanding from selling one unit to have like more and more units. And that's where the Tauri application comes in, because basically we can very seamlessly just move our code into the Tauri application, because it's the same tech stack, so you can use or react directly almost into that application. Have to do some changes, obviously, but in theory we can do that. And the way we have done it is that we use this Sidecar. We use the Sidecar for multiple purposes, actually, but in this example we use the Sidecar to handle all the API connections to all our distributed sensors, so that the front-end code in the Tauri doesn't really need to handle that. It can only access the Sidecar and get all the information unified from that part. So the Sidecar basically has a database of everything needed to create our user experience. So the Sidecar communicates with all the different units that we have, and the Tauri application can focus on making a great user experience for the user. So that means that even though we lose one of the sensors, let's say one of them goes down because of battery or some other reason, we can still use the system, because in the other one, if the node that we actually used to connect to all the others went down, you went down the whole network, for instance. But in this case, we can have like an offline status. Okay, this one went out of battery, or this one was not working anymore. And we can also also add all the events that we have got from all of these. We have a place to store them as well, so we can store them on the Tauri side of the application. So that means that we can actually start making a user experience that handles the whole network, and we can start utilizing the Tauri web framework to make this user experience fast, and we can iterate on that part very fast. And one of our teams can work on working on that part, and we can switch to other teams to work on the connection part or the audio processing part and these guys. In addition, we use it because we make hardware products. And the hardware consists of very many parts that we need to combine, and we need to scale our production, and we need to make test systems for all this. And we also started using Tauri for that purpose, so that we can write all these test components in Rust as well, so that we can start utilizing that language for that purpose as well. So we start writing Tauri applications for kind of having the view of the production workflow, so that we can ship that to manufacturers that can kind of produce our products. And we can make all the test tools with the same framework. And we find Tauri to work really well for this as well. And using the web to actually make the user experience for a factory production is really nice, I think. So that kind of means that you can build this architecture for just testing purpose as well when you manufacture. Okay, so what challenges have Squared experienced when we have kind of gone from this? So we started with this actually, let's say 9 months ago, I think. And we already have a few applications running on Tauri today that we use in production. So it hasn't taken that long to actually build it. But most of my developers come either from C++ or the web world, basically. So Rust was not anyone new, actually. So it was a bit of a learning curve to start with the Rust framework, but we ended up writing a lot of the sidecars in Rust in the end. So I think most of my engineers actually liked Rust a lot. And at least the ones that came from the C++ world already, they kind of found Rust to be an interesting and very nice language to learn. We did have some problems with system dependencies we're missing on target machines, because we install our application on other users' computer, and sometimes we had to bundle the native dependencies to support offline install. Because when we say we need Tauri on Windows, for instance, we also say we need the Webview 2 to be installed. And if it's not installed, the installer goes on the internet to fetch it. But then if it doesn't have internet, you can't fetch it. So it ended up with us, we had to embed the Webview 2 installer within our application. So in a way, we kind of had to add something to our application to increase the size. But the advantage anyways is that once it is installed, the operating system takes over the responsibility to update it. So if you do have that machine online, it says it needs to be updated. So it's just the first install that needed to be fixed like this. Some developer experience that we love. Coming from having developed C++ applications for desktop for many years, actually going into this web workflow is pretty nice, I think. So we're using Bun for running scripts and dev servers. So when you have development of the Tauri application, you run the dev server there, and you use Bun for actually running it up and down. It's very, very fast, so you can iterate on it very fast. And we use Vite for instant front-end rebuilds with the TypeScript React stack. And that means basically you can write your front-end code, save, and then sometimes you just saved and you should wait for the application, but in the instant you use to switch the modus, it was already updated. So that's kind of very different from compiling the C++ and waiting for the application to launch, kind of. So using this web technology is very, very fast and has a very efficient developer workflow. We can do that with the Rust as well. So the Rust backend supports hot reloading with this cargo watch package. So even when you just change your Rust code, save it, it recompiles and launches the new application with that Rust package inside it as well. So that is also very, very fast. So I think this developer experience is something that we like very much, and it's very fast to iterate on the app. And the backend is fully debuggable with the Rust tooling set, and you have all the cargo, all the crates that you need for Rust development, and these things. So I think that is kind of our experience, is that that's a very easy way and very fast way for us to move to develop new things. And it hasn't taken us very long to adopt to this kind of technology to work with this framework. So how do I choose if Tauri is something for my company? I would say if you do need some lightweight apps, I would definitely recommend Tauri above Electron, but there are obviously other frameworks you can also use for this. If you have strong operating system integration, I think the IPC communication and the performance of the rest is very nice, and it works really seamlessly. So I think that's one of the things you should consider at least. And if you do have security critical tools, I think having a framework that helps you make safe code is a huge advantage. So when do you want to stick with Electron? I would say in web-heavy applications, if you don't really need the backend of the application and you only use the frontend to actually access other parts or log into some other cloud service or something, I think Electron is very, very suited for that. And I also think you also more easily can get people that like that web flow as well and can kind of fastly get into that development mode. And also this, if you have heavy browser dependencies, if you use some specific parts of the Chromium, you can also think that it might be easier to use Electron so that you only have one Chromium engine to support in your code, basically. So that's kind of my opinions. But there are probably lots of pros and cons with both of them, and you should consider that when you do choose. And I also think Qt is something that you absolutely should think about, but it has some completely other things to think about. So the future is native plus web is what I think, and Electron walked so Tauri could run is what I would say. Electron came in, made the path, and then Tauri came and fixed a lot of the issues. Is my interpretation of how we have adopted to Tauri. Thank you very much. Any questions? You were first, so.
I was wondering about the security aspect. You mentioned there's a key that's used for invoke.
Yeah.
Could you elaborate a bit on that? And then the other thing that I wasn't sure I really understand is when you bundle the TypeScript or the JavaScript inside the application, would you still be able to pick into the application binary and change some of that code eventually, changing what you're calling in the backend? So you still have that sort of like vector to, communicate with the backend in a way that's not intended, right?
Okay, so the question is, the first one was if...
Could you elaborate a little bit on how the key works?
The invoke key? Okay, I'll take that one first. So the invoke key is something that is generated in the build process and compiling. I don't know the exact details on how they do it, that you need to read the documentation on. But this is kind of the whole security mechanism of this Rust. Right? So basically you have the tau and the vri that kind of builds in this on each of the Rust sides, basically. And it is the Rust communication that handles this key. But I don't know exactly the details how they do it. That I need to read the documentation on.
The second part maybe, like my understanding was you want to prevent third-party clients from accessing the backend using the same API, right? But if you already have access to the binary of the actual product, would you be able to inject some code into the actual JavaScript that's bundled in the binary to still access the backend?
So the question is if you have access to the native binary, if you can access that one and inject something into the application.
Some JavaScript in there you can actually add it.
Yeah. So basically, I think this is something that is used on the operating system side, because when you distribute this app, you sign the binary. So you can't easily modify that binary But even though you could do that, so if you bypass that signing mechanism and you use an unsigned application, you might be able to go into that one, find the JavaScript file, edit it, and then make a new binary. But that's kind of the operating system that wants you to protect from that part of the system. Yeah, but if you do accept unauthorized binaries, you risk doing that, obviously. Yeah. Yeah.
Kind of on that same path. So in Electron, is the worry like, because if you download code from the internet, obviously you have to know what it's doing, or else you're vulnerable. But is it more like, are we worried about specific third-party dependencies that are broken, or are we worried about like the user has another script on their system that's malicious that could kind of get in the way? Is that kind of
Yeah, so the question is how Electron can be vulnerable from external scripts. Very often when I see web developers, sometimes they tend to just use a framework that they reference with internet, for instance. So that is one part where you can inject something externally, where they use, okay, I just use some framework that is referenced on the internet, and I just use it directly into my application without thinking, really. That is one way you could do that. There's also ways where you can actually, if you open web pages within the application, like in iframe, that is also one way you could potentially inject something. I don't know if you, I don't know exactly the details how prone you are for that, but there are also things that you could run, like if you have inserts of certain text or something, you could potentially, that could also be injected in some way. But these are kind of things that you very often are aware of and try to avoid as much as you can. So it's not very common, I think, but there might be some loopholes in an application if you don't think about it.
And then the other question I had was, how is the web standard support with these WebKit, like platform WebKits? Because I know that.
So the question is, how is the web standard in relations to all these web kits on the platform itself? My experience with that is that they're pretty well handled, but they tend to be one version behind, kind of, if you think of it. So if you have like the modern web browser has capability A and B, which is very new, you don't necessarily have that on the embedded one. So they seem to be like a little bit lagging behind. So they're not the most modern, but that was more a problem before, I think. When you now use React and other frameworks, they kind of just wrap all these things. Before, when you had to use jQuery to kind of hold for all these things, then you were more prone for these issues, I think. And I think it's not really a huge issue. Yeah.
Another question is, you had the invoke call where you pass like the name as a string and then the arguments is just like a JavaScript object. But the Rust is that you're calling into eventually is compiled statically. So I guess theoretically you could generate like JavaScript shim functions and then generate like TypeScript types for that, so that in your editor you kind of know all of the backend calls and it all just works. Do you know if there's any support for that, or if it's like something they're considering?
So the question is, so in the invoke command, you just send a JavaScript parameters into this invoke command, so that, and they're kind of handled on the Rust side into some Rust types, basically. And the question is if there are some ways of handling that between the TypeScript and the Rust. And to be honest, I don't know exactly how we handle that. I guess it works for simple types in a way, because they're kind of created. But if it works for more other types, I'm not sure.
Well, it's more like you could automatically describe those types, generate TypeScript definitions from the Rust calls, and then have like auto-completion just work for your invoke calls.
Yeah, I believe that should be possible, but I do not know the details of it, unfortunately. Yeah.
How can you do automatic testing on the front end and the back end in that environment?
So the question is, how can you do automatic testing and front end on the back end and front end in the application?
Or in your development environment somehow?
You have some unit test frameworks that you can do that, but I have not gone into the automatic testing too much, so I can't really explain how you can do that. But I'm pretty sure there are some ways of doing it, but I do not know. So. Okay, thank you very much.